Recursion is a topic that will allow us to write methods in a different way, and it will also allow us to think of repetition of loops in a different way. This is a topic that the students sometimes find challenging, so you need to see several examples and practice, take time to become familiar with this topic. It's a very interesting and very fun topic. Now, what is recursion? Recursion is a self-reference. We are defining something in terms of itself. Now, what is that something that we are defining? For example, we are defining a method, and the method body contains a call to itself. We have seen many methods where inside the body of that method we are making an invocation to a different method. Method A is calling method B. In a recursive method definition, we have a method calling itself inside the body. And we will see very shortly an example of that. That other thing that can be defined through a self-reference is a data structure, and we have already seen such an example. For instance, when we were defining the linked list node class, recall how we defined a node. And you can pause this video and actually go and see that for yourself. We had a node carry two members. One is the actual data that the node needs to have, and the other one is a link. A link to what? A link to a node. So in other words, we are defining a class, a node class, a data structure, which has as members a node itself. This is an example of a self-reference, of a definition that is using itself. How does NonRecurring work? The key lies to a detail that we didn't mention before, and this is the fact that the method does not always call itself, or the data structure does not always link to another copy of itself. So the self-reference does not always happen. It is part of the definition, but it does not always happen. There is always a base case, as we say in programming terms. In other words, there is always a case that the reference, the call to itself, will not happen. And recursion works well exactly for those kinds of problems that we can easily split them in this way. We can have a basis case and a recursive case. Let's take a look at a few examples, and you will see that all of the examples we have chosen here are mathematical functions, functions that are or can be defined recursively. You will see that a language that supports recursion makes the task of defining such a mathematical function in code so easy. It is almost as if we just take the definition, the mathematical definition, and we copy it into code. The first example we will see is how we can generate the numbers of the Fibonacci sequence. So we want to write a method in Java that will produce the nth number of the Fibonacci sequence. If you don't remember, you can refresh your memory and look it up. The Fibonacci number n at the nth place in the sequence is produced by adding the values of the two previous numbers in the sequence. So if we add the Fibonacci number n at position n minus 1 and the Fibonacci number n minus 2, the sum of those two numbers will give us the value of the Fibonacci number n. Now, to that we have to remember that the first terms of the Fibonacci sequence are predefined, so those are going to be our base cases for our method, and in those cases the method will always return 1. However, if n is greater than 2, then we will have the recursive call. And what will that be? It will be actually two calls to the Fibonacci method. One to find the value of the number n minus 1, and the other one to find the value of the Fibonacci number at the position in the sequence n minus 2. Pay attention to this fact. Every time we write in the method code Fibonacci with some kind of argument, that means a method invocation. So the control of the program will start at the next method invocation of the same Fibonacci sequence. I know that it may be a little bit puzzling to wrap our heads around the fact that inside the method code we are actually calling the same method. We are having two method invocations to the Fibonacci method. This will become clearer at the next video, where we're talking about the role of stack in recursion and how exactly those recursive calls work. So bear with me until we complete this discussion, and shortly we will be able to understand better how recursion works. Not why it works, but also how. A second note to make here: notice that the method invocation has a smaller argument. So the initial method had n as the argument. When we are calling ourselves inside the body, we are providing argument that is smaller, n-1, n-2. This is critical for having a recursive call that works. And again, we will see more examples and we will talk more about it later. Now, the Fibonacci mathematical function is a function that is defined recursively. We're now going to discuss about a different function, the factorial function, which may not come to your mind as a recursive function with our knowledge from math. What is a factorial of a number? Say the factorial of number 4. It will be 4 times 3 times 2 times 1. What's the factorial of 3? It will be 3 times 2 times 1. We may not have it in our mind as a recursive definition, but we can define it recursively. The factorial of number n is n times the factorial of number n-1. The factorial of the number 4, for example, has inside it the factorial of 3. In this way, we can very easily write the recursive definition in Java, in code, and we always need to remember to take care of the base case, and in this particular case it is the case when n is equal to 0, and in that case the method does not call itself, it just returns the result, which is 1. In every other case we perform a recursive call to factorial n-1. Here is one more example, our last example, of a mathematical function that we can write recursively, 2 to the power of n. Let's clear the base cases first, and which are those? When the power is 0 or the power is 1. Now, how can we compute recursively 2 to the power of n? We can do that by breaking the exponent. So if the number n is even, we can compute 2 to the power of n divided by 2 times exactly that same number, 2 to the power of n divided by 2. And if the number is odd, we can have a very similar expression, just it will be 2 times 2 to the power of n-1 divided by 2 times that same number. One note that I made at the beginning when we were talking about Fibonacci, and I would like to repeat. Notice that in all of the recursive calls, the argument is smaller than what we started. For example, in factorial of n, the recursive call is calling factorial on something smaller, n-1. Same thing with the 2 to the power of n. All the recursive calls have n divided by 2 or n-1 divided by 2. It is something smaller than the original argument. To conclude, when we are writing recursive methods, we have in mind a key task. And what is that? Breaking the problem into the base cases and the recursive case. And in the recursive case, we're solving the similar kind of problem, but a smaller version of that problem. And this is the reason that the parameter to the recursive call always needs to be smaller than we started, closer to the base cases. This is the goal. Every time we are making a recursive call, we are trying to go closer to reach the base cases so that the method actually at some point returns and our computation reaches an end.